Welcome to this lecture on continuous probability distributions. Today, we are going to shift our thinking from counting distinct objects like apples in a basket to measuring things that flow smoothly like time, weight, or distance. This is a foundational topic in statistics that allows us to model the real world with incredible precision. Let us dive in and see how it works. To understand continuous distributions, we first need to understand continuous variables. Imagine measuring the height of a tree. With a standard ruler, you might say it is 5 meters tall. But with a highly precise laser, it might be 5.0124 meters. Because height can take on any possible decimal value within a range, it is a continuous variable. This is completely different from counting apples, which must be whole numbers. In probability, when we deal with measurements that flow smoothly without breaks, we use continuous probability distributions. Now that we know what a continuous variable is, how do we find its probability? For a continuous random variable, the probability of it landing on one exact, infinitely precise number is actually zero. The chance that a tree is exactly 5.00000 meters tall down to the atomic level is practically impossible. Because of this, we cannot use a simple list of probabilities for each number. Instead, we use a mathematical curve called a probability density function. This curve does not give the probability directly. Rather, we look at the area under the curve. This brings us to the most fundamental rule of the probability density function. If we want to calculate the total probability across all possible values, we take the integral of the function f of x from negative infinity to positive infinity. This integral calculates the total area under the curve. For the function to be a valid probability distribution, this total area must equal exactly 1. This represents a 100% certainty that the variable will take on some value within its possible range. If the area is anything other than 1, the curve is not a valid distribution. So, how do we find the probability for a specific range? We use this formula. The probability that our random variable x falls between the values a and b is found by calculating the definite integral of the probability density function from the lower limit a to the upper limit b. Physically, this represents slicing out a section of the area under the curve. As the gap between a and b gets wider, the area increases, which means the probability of the variable falling in that wider range is higher. If you shrink the gap to 0, the area becomes 0. Let us look at this visually. Here we have a graph of a probability density function. The horizontal axis represents the possible values of our continuous variable x, and the vertical axis represents the density, f of x. Notice the smooth bell-like shape of the curve? The total space under this entire curve is exactly 1. The shaded blue slice represents the specific probability of the variable landing between the boundaries A and B. By calculating the area of just that blue section, we find our exact probability. While the density curve shows us the probability at a specific spot, we often want to know the running total of probability up to a certain point. Imagine filling a bucket with water from a hose. The rate at which the water flows out of the hose is like the density function. The total amount of water that has collected in the bucket at any given time is the cumulative amount. In statistics, this running total is called the cumulative distribution function. It answers a very simple question. What is the probability that our variable is less than or equal to a specific value? To find this running total mathematically, we use the cumulative distribution function, denoted by a capital F of x. This formula defines it as the probability that a continuous random variable x takes a value less than or equal to a specific number x. We find this by taking the integral of the probability density function from negative infinity all the way up to our target value x. Because we are using x as our stopping point, we use a temporary dummy variable, t, inside the integral to avoid confusion. As x moves further to the right, we accumulate more area, so the cumulative function grows larger. This formula shows the reverse relationship between the two functions we just learned. If you already have the cumulative distribution function, capital F of x, and you want to find the probability density function, lowercase f of x, you simply take the derivative of the cumulative function with respect to x. By the fundamental theorem of calculus, the rate at which the accumulated probability is growing is exactly equal to the density at that point. This means the density function is just the slope of the cumulative function. If the cumulative probability is rising steeply, the density is high. Because the cumulative distribution function represents a running total of probability, it has several strict rules it must follow. First, it is non-decreasing. Because probability cannot be negative, adding more area as we move to the right can only make the total stay the same or go up. It can never go down. Second, it is right continuous, meaning there are no sudden jumps or breaks when approaching a point from the right side. Finally, it has specific limits at the extreme ends of the number line, which dictate how the accumulation begins and ends. Let us look closely at those extreme limits. The first limit states that as x goes to negative infinity, the accumulated probability drops to 0. This makes perfect physical sense because there is no area accumulated before the very beginning of our range. The second limit states that as x goes to positive infinity, the cumulative function reaches exactly 1. This means once we have swept across the entire possible range of values, we have collected 100% of the probability. Every valid continuous distribution must obey these two boundaries. Let us put these concepts into practice with a concrete problem. Suppose we are given a continuous random variable x with a probability density function defined as c times x squared for the range 0 to 2 and 0 everywhere else. Our first goal is to find the value of the unknown constant c. To do this, we must use the fundamental rule we learned earlier. The total area under any valid probability density function must equal exactly 1. So, we set up the integral of our function from the lower limit 0 to the upper limit 2 and set it equal to 1. Continuing with our calculation, we pull the constant c out of the integral and apply the power rule for integration. The integral of x squared is x cubed divided by 3. We then evaluate this from 0 to 2. Substituting the upper limit 2 and the lower limit 0 into the expression, we get c times 8/3 equals 1. Now we have a simple algebraic equation. We multiply both sides by 3 and divide by 8 to isolate c. We find that the constant c is equal to 3/8. Our complete density function is now known. Now that we have our complete probability density function, 3/8 x squared, our next goal is to find the cumulative distribution function, capital F of x. We do this by integrating the density function from the starting point 0 up to a variable point x. We use t as our dummy variable inside the integral. We integrate t squared to get t cubed over 3, multiply by the constant 3/8 and evaluate from 0 to x. The 3's in the numerator and denominator cancel out, leaving us with x cubed over 8 as our final cumulative distribution function. Finally, we want to find the probability that our random variable x is between 0 and 1. Because we just found the cumulative distribution function, this calculation is incredibly fast. We do not have to perform a new integral from scratch. We simply evaluate the cumulative function at x equals 1 because f of 1 gives the total probability from 0 up to 1. Calculating the cube of 1 leaves us with 1 over 8. Converting this to a decimal, we get 0.125. Physically, this means there is exactly a 12.5% chance that our variable will land in this range. Now that we know how to find probabilities, we need to describe the center and the spread of our continuous data. For discrete data, we found the mean by multiplying each value by its probability and adding them up. For continuous data, we do the exact same thing, but we replace the summation sign with an integral. The mean, also called the expected value, acts like the physical center of mass of the probability curve. If you cut the curve out of cardboard, the mean is the exact point where it would balance perfectly on your finger. The variance then measures how spread out the curve is from that balancing point. Here is the formula for the expected value, or the mean, denoted by E of x. We calculate it by taking every possible value x, multiplying it by its density, f of x, and integrating over the entire range from negative infinity to positive infinity. This integral perfectly balances the values against their probabilities. If the probability curve is shifted to the right, the larger x values get more weight and the mean increases. This gives us a single number that represents the average expected outcome if we repeated an experiment many times. To find the variance, we need two formulas. First, we calculate the expected value of the square of the random variable, e of x squared. Instead of multiplying the density by x, we multiply it by x squared and integrate. This intermediate step is a crucial building block. Next, we use the variance formula. We take that expected value of the square and subtract the square of the mean we found earlier. A large variance means the probability curve is wide and flat, indicating highly spread out data. A small variance means the curve is tall and narrow, tightly clustered around the mean. Let us calculate the mean and variance using the exact same distribution from our previous example, where the density function is 3/8 x squared for the range 0 to 2. We start by calculating the mean, E of x. The formula requires us to multiply the variable x by the density function and integrate over the valid range, which is from 0 to 2. To make the math cleaner, we combine the x terms to get x cubed, and we pull the constant 3/8 outside the integral. Now we are ready to integrate. Applying the power rule, the integral of x cubed is x to the power of 4 divided by 4. We evaluate this from 0 to 2. We substitute the upper limit 2 into the expression. 2 to the power of 4 is 16. Simplifying the fraction inside the parenthesis, 16 divided by 4 gives 4. Multiplying 3/8 by 4 gives 12/8, which reduces perfectly to 1.5. The mean is 1.5. Physically, this tells us that the center of mass of our probability curve is located exactly at 1.5. Next, to find the variance, we first need to calculate the expected value of x squared. We multiply x squared by the density function and integrate. Combining the x squared terms gives x to the power of 4. We again pull the constant 3/8 to the front. The integral of x to the power of 4 is x to the power of 5 divided by 5. We evaluate this from 0 to 2. 2 to the power of 5 is 32. Substituting this in, we multiply 3/8 by 32/5, which gives us exactly 2.4. Now we have both pieces needed for the variance formula. We take the expected value of the square, which is 2.4, and subtract the square of the mean, which is 1.5 squared. Squaring 1.5 gives us 2.25. Subtracting this from 2.4 gives our final variance of 0.15. This relatively small number indicates that the values of this random variable tend to cluster fairly closely around the mean of 1.5, rather than being wildly spread out across the entire 0 to 2 range. Let us summarize what we have learned. Continuous probability distributions are the backbone of modern science and engineering, allowing us to handle variables that can take on any decimal value. We use the probability density function to see the shape of the probabilities, and we integrate it to find the actual chance of an event occurring within a specific range. The cumulative distribution function gives us a convenient running total. Finally, by integrating, we can find the mean and variance to understand where data is centered and how it spreads. You now have the tools to model continuous realities.